The idea for integration is what we said yesterday, okay? Remember, yesterday or 2 days ago, no, yesterday, we were talking about slope fields, and we said, how do you get the derivative? Remember that? How do you get the derivative? So the whole concept comes about. The whole concept comes about where if you have a rate of change, or let's say dy dx, let's say dx dt. Let's start with dy dx. And we're told that the rate of change is something like, what did we say yesterday? 1 over x. How do you get 1 over x? What derivative do you take that gives you 1 over x? ln. So if you want to figure out what the function y is, yeah, it's just ln x. But what do we always have to add at the end? What did we say yesterday? Some constant. Again, because this constant could be any number. This could be 5. And when you take the derivative, the 5 drops off. This could be 7. And when you take the derivative, the 7 drops off. So this is just some number. It's a numerical value, the constant. A lot of the problems in integration is to determine the constant. The whole goal of integration sometimes is, yes, we can have a family of functions, like we showed yesterday. Remember all those curves on top of each other? That's a family. We want to figure out which one of those families is our answer. That's where we find the constant. So our goal here, okay, is to do the antiderivative. The antiderivative and figure out the constant that really captures the antiderivative. Because this is just a family of functions. C could be any number. What is C is the question, okay? So that's what our goal is going to be the entire second semester, really. Now, we're going to talk about many representations of integration. We're going to talk about, remember how the tangent was the derivative? We're going to talk about something called the area underneath a curve. That's going to be the integral, or the integration of it. So we're going to talk about geometric representations as well. Kenneth.
Is there no other, because you know how, isn't C just the shift, up and down the x-axis?
Yes,
but then, the y-axis, I'm sorry. But then what about,
y-axis,
y-axis. But then what about the x-axis?
That doesn't actually matter, believe it or not. It doesn't even come into play. You're going to see a little bit later, though, that C is not always going to be a plus. Sometimes C could be in front, and then it's a multiplier. So that would determine the width of the graph.
Yeah.
So it changes. It doesn't really change the location this way. Okay?
Okay.
There are times where C could be like a function of something else also, but that's beyond this course of calculus. That's like higher level of calculus stuff, where C is a function of X.
We're not worried about that.
Okay? But we're looking at when C is a number for now.
Okay.
Again, you gotta learn the basics, right? It's like learn how to add. If you don't know how to add, then you can't do stuff like this, right?
Learning how to fly.
Learn the basics.
So,
At the same time, that's wild.
Let's do an example. Let's say we had,
Like this is the basics. That's terrible.
let's say we had,
7.
I don't know if Facebook can put the terms notice jumping off a roof. So you're saying how on Facebook they have a section where you had these key terms and they say
I said this?
Yeah, you're talking about how you say suicides, you say go jump off a roof, something like that.
Yeah.
So on Facebook I'll put jumping off a roof.
Kenny,
And so I wanted to see if I would
what
get
are you
help.
doing, man? And what happened?
Huh?
Did you get any emails yet?
No.
Yeah, we can't write you.
They don't want to help me. It's just probably help a little bit.
You're funny, Kenny. All right. So let's do a proof. Okay? Very simple. Not a proof like statement reason, guys. A proof meaning we're just going to prove how an integral works. That's all. So let's say y equals x.
We gonna get it to work. Oh, that's cheating.
What are you trying to
It's balancing.
do? So let's say we have the graph y equals x. Now, if I want to know what the integral is of this, what the integral is. Okay, so say this is my y value, y equals x. I want to know what a new function is. How do I go up a step again? What do I make it?
You make it.
1 over 2x?
Okay.
1 over 2x to the second.
Very good.
That's what I meant.
So the integral of this would be 1/2 x to the second. Remember, how did you get this? If you take the derivative of this function down here, you take the derivative of that, you get back to this.
So with this one, we're gonna start just
Just
from
trying
the
to get you
regular.
thinking, that's all right now.
Oh.
We're just going through thoughts about integration. We'll get to the formalities of it soon, okay? But I'm just getting you thinking. Now, if you have a graph of this function up here,
Take the paper.
what does y equals x look like? A line. What kind of a line?
Vertical.
Rabbit.
Diagonal.
Oh, I'm sorry.
Come on. Slope is 1.
Right?
This is the slope of 1, a y-intercept of 0. It's at a 45-degree angle. Come on, people. Thank you, Edgar. Save me. I was
We're such
losing
at a
my
high
mind.
level that we, stuff.
You guys are all thinking of other stuff, I know. If it's a number, then it's a horizontal, yes. You all took the derivative or something, I don't know. All right, so let's say for now that this is a triangle. And if I know that this distance here is represented by x, would you all agree with that? That's what we call that? Don't we call this the x-axis?
Yeah.
So I can call that distance x. Now, if my slope is 1, what is this distance also?
1. No.
Okay, y, good. This is the distance y always, good.
We can use
But if the slope is 1, what can you tell me?
It's
What is it? Same as x.
I was gonna
Again,
tell
if
you
the
that.
slope is 1, remember I just said 45 degrees. That's why I wanted you to think. Aren't these the same?
I
What kind of a
was gonna
triangle
say
is it?
that.
45, 45, 90. The isosceles right triangle. So, as Edgar just said a minute ago, this is y, as Karen said, sorry, but then as Edgar commented also, this is x. So, call this x, please. They're the same in this case. Tell me what the area of that triangle is, everybody.
Area
Area of this triangle.
1/2 x y.
xy, but y and x are the same, right?
Yeah, x.
It's really 1/2, yes, xy, but it's really x squared. Okay? The area under the curve is the same thing as the integral. Again, take a look at this. You have 1/2 x times y, right? But y is really x.
Oh, I see what we're getting.
So you have 1/2 x times x.
So we look under the curve, right?
And this is the area underneath this curve. That's what we're shading in right now. That's that area. Well, you get 1/2 x squared. Didn't we also get 1/2 x squared here? We looked at my class. We also got 1/2 x squared here.
1 second.
So if you
Talk along.
if you look at a curve, we call it a curve even though it's a line. If you look at any curve and you find the area under that curve, it's the same thing as the integral. Okay? So yesterday we talked about it, we called it the antiderivative because it meant you moved up one level. You went from the derivative to the real function. Today we're calling it the integral. It's also called the area under the curve. So let's go ahead and do that. Let's write this.
What?
Did I spell it wrong? I might have spelled it wrong. Anti. Nope.
Yeah, there we go. He spells it backwards. It's not easy to do.
Antiderivative. It's actually true. You guys ever played Cranium before?
What?
Cranium, the board game?
Nope.
It's like Taboo or one of those kind of games. Cranium's awesome. One of the things you have to spell the word backwards, and they give you crazy words. Like spell vocational backwards, like something like that. And the hard part is that you're in teams, so everybody has to do a different letter. So if there's 3 people on the team, it's like L, then the person saying A, then N, and you have to go through one after. It's actually tougher than it looks.
We should
Alright.
try it.
So this is what I want you to know. This is the key to the entire second half of the year, guys, okay? Again, the antiderivative is also called the integral, which is also simply the area under the curve, okay? And we're going to talk about when we use the area and when we use the antiderivative and when we use something called a definite versus an indefinite integral, okay? They're different terminology, but this is the general idea. Say again? Correct, when you're given the initial conditions. Yes, absolutely.
What about, Charles, you're the Nicolas Cage of math, right?
Say again?
You're the Nicolas Cage of math.
I'm the Nicolas Cage of math. What does that mean?
I don't know.
What is he?
Explain, elaborate, Kenneth.
Oh, okay.
National treasure?
National
Because why?
treasure.
Because he knows his stuff?
Yeah, I was saying, yeah, pretty much.
Because he can find anything.
That's a
or
good
something?
movie.
I
enjoyed it.
That's what he said. He said you can find anything. No matter where it is, how you gotta get to it.
Yeah, it's pretty
Oh, I
good.
get it.
All right, let's draw a quick axis.
That Kenneth.
Draw a curve, please. Doesn't have to look like exactly like mine. Draw any curve. You can pick whatever you want. Now, if I wanted to know, let's say I was looking from A to B. Okay, this curve goes on forever. It might go on, have other behavior later on, but I'm looking from A to B. And I want to know, what is the area from A to B under that curve? It's a pretty weird shape, right?
Yeah.
Agree? What can we do? We did this in physics. I know that already. We talked about this in physics.
The rectangle.
Good. Put a bunch of shapes underneath it that could approximate. So the standard way to do it, the first thing everybody ever thought was to put rectangles.
No.
Start like this.
Start with circle.
Start with a bunch of rectangles.
You want us to do this too?
We did this in physics, I know that already.
Who started this anyway?
Okay, and go all the way to the end. Sorry, one sliver at the end. Okay? I know, they're all missing, I understand. From A to B only, Karen, A to B. Again, we're trying to figure out, guys, by the way, this is the symbol. The symbol we're going to use all here looks like this. That means integral. And from A to B, okay, means that. That's all it means. Yep. You familiar with this, right?
I didn't see this.
Stop shaking your legs.
You understand the top and bottom while you're there? Lower limit, upper limit? Huh? Like, over here, you mean?
Really?
Here and here? Or here and here? I always put it above and below. You can put it the other way, but I would recommend putting above and below. That's the way I was taught. Yeah, I mean, if you put it over here, you're saying like B and A like that?
Isn't that great?
Is that what you're saying? That's really only used on computers when they're running out of room on the page or running out of room on the line. The general form doesn't. Alright, so you might say, okay, well we're looking at this and we're saying that we can put these rectangles on here, but there's all these missing pieces. So let's go ahead and color them in blue. You know you don't have colors on your paper, but shade these in, please.
So what about, oh, okay, only from A to B, I get it.
They're generally triangles. They look like triangles. They're not exactly, because we have little slivers.
You're right.
Okay, after that, I mean, you got a little blue in here. You would probably have a little bit of blue here unless it was a flat line. If the line was perfectly horizontal, you wouldn't have any blue in there. There's a little bit of blue in there. Okay? Again, we are looking from A to B only. That's why we didn't go further. So this area over here doesn't matter. Now I'm going to color in the rest, or I'm going to cross-hatch the rest in green, so you can see. So if you're doing this, shade and then cross-hatch, please.
But isn't that
I'm going to explain, guys. I'm just showing you, hon. Just trust me for now, please. Because we're going to use this, Janice, we're going to use this to approximate the integral, but I'm trying to show you that these are missing pieces. That's what I'm doing. If I could figure out the exact area under here, you would have the exact answer. And that's where the symbol comes in, and that's where that thing comes in where we did the antiderivative, I got the C, that's where that's going to come in. But for now, for today's, all you think is this. This area is a pretty good approximation. We're missing these blue spots. Would you agree?
Yeah.
If you were to give me a value, how much percent of the area does the blue make up, would you say?
Percent?
Percent of the whole area,
7%.
of the whole area under the curve, how much does the blue represent?
10%.
Less than 10%, I would say. If I were to give a roundabout, I would say less than 10%.
About 7%.
So what we're saying is that we're pretty much, we have 90% of the area. Would you agree? So for a long time, people said, okay, we have 90% of the area, approximately maybe. So we'd say this represents 90%. We'd find that area. So let's say this area was, let's say this was, these were all 2s. Okay? Let's say all these widths were 2s except the last width was a 1. And let's say that this height was,
Could we just
put a bunch of heights down.
Can we just say it was all 2 because we're writing on graph paper? They are
Sure,
the
if
same.
yours are all the same, guys, and you have all the same, then call this last one 2. Call them all 2s if you want to. Mine looks a little smaller, that's why I call it a 1. But if all your widths are the same, they should be for this method, call them all 2s for now. Doesn't really matter because later on we're going to see that the widths can change, so it doesn't matter which way you have it. Let's say this height is 10, 10, 10, those are all the same heights. Then we'll say this height is 9, this height is 8, this height is 6, and this height is 4.
Oh, let's get
Okay? I'm giving you the heights of each, the heights. So that's a height of 4, this is a height of 6, this is a height of 8, height of 9, 10, 10, 10. If I could figure out the area of all these, and I know that that's 90%, I can write a proportion to give me 100%. And this is not something that any calc teacher ever teaches, but to me it makes sense. I'm trying to introduce it this way. It's a little different. So if I knew this, 2 by 4 is 8, 2 by 6 is 12, so I know these are all 2s right here. So if I could find the height of the sum of these, it's really, what am I doing? I'm doing 2 times 4 plus 2 times 6, 2 times 8, 2 times 9, 2 times 10, 2 times 10, 2 times 10. You all see that? I'm just finding the area of each rectangle. Can't I really factor out a 2? Think about it that way. They're all multiplied by 2. So I could just add all these up and then double it also. 10 plus 10 is 20, 30, 39, 47, 53, 57. 57 times 2, 114.
Total area of this rectangle.
Okay? That's the total area. And we'll say for now units squared, because we don't know if it's inches or not. Again, it's the same thing as if I did 8 plus 12 is 20, plus 16 is 36, plus 18. I don't want to keep going. It's going to be 54 and keep going on and on. Okay? 54 plus another 60 gives you the 114. But again, you can add them separately or factor out the 2. But the idea is this. If 90% represented 114, what might 100% represent? Or what might be the real area of this, right? So then you would say, okay, 90%, but I won't use the percent because I'm doing proportion. 90% means 90 over 100. Well, okay, and 90 represents 114, so call that x. We can do it that way, that's fine. Okay, and cross multiply. This was a way for a long time that people estimated areas. They said, how much are we missing, right? Well, we might want to take a look and say, okay, there's a proportion. 90% is representative of 114. Exactly, and that's what we're going to talk about.
Like, we don't know if it is 90%.
Exactly, exactly. And we're going to talk about soon how we can change this shape into not rectangles, but other stuff. Or maybe we can make the rectangle skinnier and we'll lose less material. And we'll talk about that. So here, if I cross multiply and solve, what do you get for x, guys? Okay, and again, please put the symbol here as an approximation, and it's units squared. So for a while, and that's not x as in x location. If you want to call this A, if it makes it easier, by the way, for area. Okay? We call that x because x is any variable, right? But I don't want you to confuse that. It's not x like on the x-axis. This is the actual area we're estimating. So our area estimate is really 126 if we're looking at percentages. Now, let's look at the same curve. Okay, so the same curve now. So draw it again, please. From A to B again. And now, instead of that, let's make skinnier rectangles. Okay? So let's make rectangles that are super skinny. See what I'm doing? So I extend from here, watch. Extend from the last rectangle up until you hit the curve, come over, drop down. Up to the curve, over, drop down.
But doesn't the average, like the areas, even though they're smaller, equal the same thing?
It should, but it's not going to because look how little is missing now, Kenny. Remember how much was missing last time? That's only probably like 2% missing. So we're going to realize that for this one, our actual area of the rectangles is getting a better approximation. Okay? So continue this, please. The rest of this, you're on a flat line. Everybody see that? God bless you. Okay, the rest of it. Oh, sorry, only A to B. Sorry. Whoops. See, even I okay, only A to B.
A, B to C.
What's the saying for Pringles? Once you pop, the fun don't stop? No, never heard that commercial?
I've never seen commercial.
You know, Pringles, Mr. Howard, Pringles got lazy. They just switched it to, you know, you can't take one.
Color in your areas, please, that are missing. Okay? It's probably little bits in each spot. But again, just look at the difference already. Do you guys see the difference here? And we can, I'll show you on GeoGebra how you can change the width and it gets more accurate, how we can do other approximations. But this is the general idea. So here's one graph on the last page. Look at all that missing area. And here's the other graph on this page. Much less area is missing here. So our rectangles now give us a better approximation. Everybody see that? So here's what we want to write down. As the width of the rectangle goes to 0, or as it gets smaller, the approximation, it's a limit, very good. The approximation gets more accurate. I'm just using words now. We'll use symbols in a minute. As the width of the rectangle, or as it gets smaller, the approximation gets better. Clearly, the width of the rectangle can never get smaller than 0, because then the width would be negative. And if the width were actually 0, it wouldn't work, right?
Yeah.
If the width of a rectangle is 0, the area is 0. So this is where limits come in. Remember how the derivative was a definition of the derivative was a limit also. We are really trying to figure out the limit.
How close is it to 0?
The limit as delta x goes to 0 of delta x, okay, delta x times this f of x for all values. again, the height of the function is f of x. The height of the function is f of x. The width of the function is delta x. So if you ever want to figure out, okay, well, I want to see the height times the base, take these two and multiply them, write it like this. And if you could figure out the limit of this, as delta x goes to 0 really, you'll be able to find out the exact area. Okay, you'll be able to find out the exact area. If you can sum these, so in the front here, put a sum symbol. So it's the sum of all the areas of f of x from, we could say, I equals 0. Let me lower it a little bit so you can see. From I equals 0, I'll tell you in a second what it means, to n. Okay? From I equals 0 to n, where n is the number of rectangles in the diagram. So, I'll explain in words. Hold on. So, from 0 to however many rectangles you have. So, this number might be like 10. So, you'd say you have 10 rectangles. You want the limit as the width goes to 0 of the width times the height. So, you want it to keep going up. You want it to have smaller and smaller rectangles. So, you want n to really go to infinity. You want to have as many rectangles as possible. Remember, n is the number of rectangles. If you can have an infinite amount of rectangles, then the answer is pretty much exact. Now let me show you with GeoGebra what this means. Again, it helps a lot with the illustration I'm about to show you here.
Yay, GeoGebra!
I can post a program, sure. Guys, if you go to GeoGebra.org and you go to a GeoGebra blog or forum, all these programs are there. Just type in GeoGebra files on Google, you'll find a database of all these files. A lot of them I don't make. Okay, I would say I probably make about half of mine. Come on.
What do you mean when you say file?
What do I mean by file? If you type in GeoGebra file on Google, people already make all these files. These are files here. So watch, I'll show you what I mean. Instead of derivatives, we're on integrals. So where's my integrals? And what I want to talk to you about today is just the integral and the area under it. So these are all files. Some of them I made. I did not make the 3D one. That's crazy. This one's a lot of coding. I don't know that much coding to do it. Right. So I downloaded it offline, and I looked at the file. Sure, they're all freeware. They're free. People put the guys. GeoGebra is a free shareware. They allow anybody to use.
So can we put
people that make them post their files online, and then you take them down.
So can we put these on our calculators?
No, they don't go to calculators. But you could have programs on calculators, and we're going to use them. Have you seen them yet?
Get up, Google.
Have you seen them yet? Programs? What keyboard?
You know.
I don't know. I don't know. We could check the clause. Anyway, so what we want to do is look at something called a Riemann sum. Okay, you want to look at a Riemann sum. All right, so do you see all these rectangles? What we just did a minute ago was the left Riemann approximation. Okay, and we talked about this, yes, we did look at this.
But see, their rectangles go over the line.
Well, I'm going to show you how that works. Let's look at our curve, though. Ours was square. So let's bring this up. Now do you see? Okay, so this is what we just did a minute ago. From A to B. From here they're going from 0 to whatever the endpoint is. And the endpoint is set in the program. So if we open up the program and define the endpoint.
Now could we change the endpoint?
We're going from, where is it? 0 to 5. There it is. A and B. See A and B right here, guys? If A was 1, watch what happens. Now it only goes from 1 to 5. So the rectangles start right here at 1. If the area was from 3 to 7, it goes simply from 3 to 7.
So back to 1.
Oops, I put a 1, sorry. From 3 to 7, and I'll grab the graph and move it over so you can see. And now we're going from 3 to 7. So you get the idea so far? Okay? Now, watch what happens. N is the number of rectangles. As n goes down, oops, let's grab the pointer. As n goes down here, you're going to see it gets less and less accurate. The exact integral is 105. What's our estimate? 80. 79, right? So we're looking at about 80%, a little less. Okay? As we go over, though, from the left, now look at the left. Now it's become 90, and the exact is still 105. The exact's not going to change, because the exact answer. As I go over, from 89 it gets to 92. Watch what happens now, as I keep going here. Look at all those rectangles now. See, they're all rectangles in there. Now look how close it is, because all these little errors are here now. As I keep going, as I go to infinity, it would become exact. So if I change n's parameters, I can make n anything. Here, watch. Let's change n. make the max 2,000. Okay? So we're at 40 now. As I keep increasing the value of n, what happens? It pretty much colors in. Look at the estimate and look at the exact. I mean, it's off by 0.07. As you keep going, it's closer and closer, but it's still never going to be there because it's an estimate. It's always an estimate.
But how did it go
not
over?
there now. The midpoint looks like it's there because it's 3,3, but if you continue the decimals, it would not be there. You can never be there. That's the idea of an estimate. It's a limit. You're approaching the answer, but you're never going to get to the answer. So as n goes to infinity, your answer gets closer and closer. But our problem right now is to look at n on a smaller scale. So let me change that. It didn't work. Let's go this way. Now, the next lesson that we're going to talk about next week, to give you a preview, and we'll start looking at this geographically, but we're not going to do anything by hand. That's why you think about this weekend.
Geographically?
Geometrically. Thank you. Is looking at the difference between left and right approximation. So, notice, I went up to the curve. I hit the curve on the left side of the rectangle, and then I moved over. I hit the curve on the left side of the rectangle, and I moved over. And these were all underestimates, right? Now, if I do a right approximation, I hit the curve on the right side and go over. So all these rectangles are overage. So notice, the answer is 105. The right approximation is over, because these are all overages. The left approximation is under, because these are all under. If you look at the left one, these are all under. You're missing them all. So if we go to this thing called the midpoint, it becomes the closest. Because what happens, guys?
Oh.
What's happening every time you have an over?
Cancels out.
Cancels out with what? The missing. Very good. So the over. So the over is here. Sorry, the under. So the over is there. The under is right there. So they're canceling each other out. Okay? So you're missing the area here, but you're gaining the area there. So when you use a midpoint approximation, it gets to be much closer. Now, if we have small value of n, it's not that good still. I mean, the midpoint is 105. The over is 105.33. It's close, but it's not even close to exact. The minute we get here, it pretty much becomes exact to 2 decimals. Now, why does this work so easily for us? Because it's x squared. X squared is a very simple one. Let's go ahead and take a look now, instead of x squared, at something like sine of x. And we're going to have to obviously change our scale here. I know that the sine curves goes from 1 to 1, so I changed my domain from range from -2 to 2. So, if we're looking between two curves here, notice, oh shoot, I shouldn't have done this yet. See how that's negative, guys? See that? Why is it negative?
Because under the 0.
The area under the curve is more than the area above the curve. We haven't even gotten to that yet. It's a whole other theorem. But the area under the curve is considered to be negative. Okay? And we'll get to that. But for now, let's go back. Let's do 0 to 2, so we don't have to run into that.
X-axis, you mean?
Yes.
Okay.
Sorry, I said under the curve. You're right, Kenny. Say that again, Kenny.
Under the curve, under the x-axis.
Yes. Again, he's right. It's under the x-axis. Okay. So from 0 to 2, and let's zoom in a little bit. Let's go on our... It's broke, though. It broke this morning. It stopped running this morning. I was like, you gotta be kidding me.
You
All right.
Take it out?
I realized that as I got to school. It says that it's 11:30. It's 56. So,
10 more minutes.
if we had a midpoint approximation here, we're going to see that the midpoint is still pretty close, generally speaking. Okay, but again, for this one, as we continue to increase n, we see that we get the exact value. For a sine curve, for a sine and cosine curve, think about this now. We talked about integrals being, how did you get to a sine curve, right? So, we talked about yesterday, cosine, the derivative of cosine is negative sine, right? But we have a positive sign here. And if this is, we want to find the integral of this positive sign, we're going to go back up to negative cosine, actually. So for this kind of a problem, the hard part is that your answers are going to be with pi's. Okay, because your limitations, you know how we call it a to b, 0 to 2? It would really be like 0 to pi over 2, or 0 to 2 pi. That's what those values would be. It's going to be in terms of pi. Okay? Now, if we have something instead of this, like sine of x with e function, where now you're going to see it's going to get much less accurate. For this function, from 0 to from 0 to 1.5. If we go back to our 2 or 3 rectangles, we see that now we're off by a pretty decent amount this time. It's not as close as it was last time. But as we go further, again, it's going to get closer and closer. Depending on your shape, each function has a different level of accuracy. Remember how last week we talked about propagated error? We said how if the radius of that ping pong ball is off by just a little bit, the volume is off by a good amount more because you're cubing the radius. We talked about this with linearization and the idea of a differential. The same idea goes here. Depending on your function, the error is more or less. And that's one of the things that we're going to start to do. And later on when you go on to calculus, you learn how to diminish the error. Do you know how we're getting closer and closer to the real thing? It's the same thing as saying, I want the error to get lesser and lesser. So you could have the limit as the error goes to 0 as one thing, or you can think of it as the limit as n goes to infinity. Again, you want the error to be non-existent. So you can think about it as the limit as the error, or e, and we call that small delta here. Okay, we call that the error. Usually you have this, or you have epsilon as the error. So later on we're going to learn how, as the error gets smaller and smaller, our answer gets better and better. We want these errors to cancel out more and more. So we want the limit as this epsilon goes to 0. Okay? Or in our case, delta would be the delta, this one, as that goes to 0. This delta here really represents this width across. That's what they use. But we're not going to go into crazy detail, but I want you to know the idea. Because later on when you go to college calculus, even when you do all the topics in AP Calculus, there's still stuff when you get to college that wasn't covered in AP. So like we're covering Calc 1 and Calc 2, but there's going to be additional stuff. So again, what's on Monday, guys? Remember.
The test.
Review.
Oh.
Tuesday is the test.
See, I would have
quiz. You guys.
It's a concept.
It's all, no, it's your test. Tuesday is your test on applications of derivatives. We talked about this. We're done with derivatives. We did derivatives, then we did applications. I'll put it on Facebook today. Look online, okay? Remember, guys, those who weren't here, those who were not here, did everybody get it?
Yeah, I'm going to start looking at the
packet that was over here. There's a practice packet, practice test for review for derivatives. I gave it out 2 days ago.
Oh, if you gave it out, I got it.
Put it over here. If you were here, if you were not absent, you have it. There's a packet on review. I can put that on Facebook also if you should. I mean, I'll be able to go for half an hour, then I go before. I think before I go downstairs to Miss Schleicher. I mean, if you're going to be here at 5, so I can order you then, but that's late. I know you like to go early. If you want to check between 3:30 and 4:30, I don't think we'll have a lot of people up here. So that might be a good time. Or you want to go over? I mean, we're going to review on Monday still, but if you have a specific area you want to look at, bring it. Well, you need to pick one then, because we're going to have half an hour. On Monday, we're going to review, we're going to do problems. Today, if you want help, pick a topic to go over. Okay? You got to do some homework.
I got the music list.